Hello, I'm Sanjana and today we'll be discussing about processes. So the topics that we are going to cover are what is a program, what is a process architecture, process control block, process state, and process scheduling. Let's begin. How do you tell a computer to do a specific task? We give the computer a set of instructions to perform the required task. This set of instructions is called a program. A program is generally written in a high level language like C, C++, Java, Python, which a computer does not understand. So we pass the program through a compiler which compiles it and converts it to a binary code or a machine code which the computer understands. So now we have a binary code for the program written in a high level language, a program that is ready for execution. But is this enough? No. For a program to execute, it needs to be loaded into the memory and requires some resources. The operating system, the OS, will do this task. It will load the program to the memory and allocate it the required resources. Then the execution begins. A program in execution is called a process. A program is passive while a process is active. So till the program is sitting in the memory and it's not executing, it is referred as a program, and as soon as its execution begins, it is referred as a process. Process architecture. Process architecture has four elements: the stack, the heap, the data, and the text. The stack stores the temporary data like the function parameters, return addresses, and local variables of the process. The heap contains dynamically allocated memory which may be processed during the runtime. It contains the memory that is allocated to the process for it to be processed. Data. It contains the global variables associated with the process. And text stores the code that the processor would be executing. So the stack stores the temporary data like the function parameters, return addresses, and local variables of the process. Heap contains dynamically allocated memory, the whole bunch of memory which would be processed during the runtime. The data contains the global variables associated with the process, and the text stores the code that the processor executes. Each process is represented by a block called the process control block (PCB), also referred as task control block (TCB). Process control block can be thought as an ID card of the process. Like in school, you have a ID card which has the roll number, the contact details, the class, division, about the student, so that it is easier to identify the student in a group of students. So similarly, PCB is a data structure that keeps track and stores all the information related to the process. So a basic structure of a PCB is like it has a process ID, a program counter, a process state, register, scheduling information, memory management information, a list of open files, I/O devices, accounting information, and many more things that are related to the process. Let's discuss few of its terms. Process ID. When a process is created, the OS will give it a process ID, the PID, so that it can uniquely identify the process. Program counter. This stores the address of the next instruction that is to be executed in the process while it is executing. Process state. This has the state in which the process is currently. We'll discuss the different states like the new, running, waiting states in the video ahead. Registers. This stores the data of all the process-centric registers like the general purpose registers or the index registers, base registers that are used in the following process. Scheduling information. This stores the scheduling information like the queue pointers, priority, all that is required for a process to be scheduled. Memory management information includes information related to the memory that is allocated to the process. Accounting information is basically related to the clock, so the clock time that is elapsed, time limits, CPU time used, etc. The I/O status information is like the information related to the input-output devices allocated to the process, the files that are being used, like the list of open files, the list of closed files, etc. When a process executes, it moves from one state to another. Process states. So, um, there are typically 5 process states: new, ready, waiting, running, and terminated. So, when a process is created, it is kept in the new state. When it is ready for execution, it is brought to the ready queue, present in the ready state, and from the ready state, it is dispatched to the running state. And from the running state, it can either exit when it is completed and go to the terminated state, or it can go to the waiting state if it requires some other resource, or like some other resource to be used, like an input output request. And when it completes that operation, it goes back to the ready state, and then after going to the ready state, it is dispatched again to the running state to complete its execution. And from the running state, it can go to the ready state in case if it has been interrupted by some other process um, while it has been executing. So it does not need any other resource to be accessed, but since it has been interrupted by some other process, it has to vacant the CPU for that process to for that process execution. So it is moved to the ready state, and after the process which has interrupted it has completed its execution, the process would be brought back to the running state and it would complete its execution. So the long-term scheduler would bring the process from a pool of, like, there would be multiple processes present in the computer, right? So from there, the long-term scheduler will bring the processes from there to the ready state, and from ready state, the short-term scheduler will dispatch the process to the running state. And suppose since there are multiple processes going on, and there are multiple processes are requesting um, for a resource, like some device or resource to be used, so they would be transferred to the waiting queue. And suppose this waiting queue gets filled up, then where would the process go? So if a waiting queue is filled, the process would be swapped out to the suspended wait state. This will be done by the medium term scheduler. So if a waiting queue is full and the process wants to enter the waiting queue, there is no space to accommodate that process. So the medium term scheduler would swap out the process to the suspended wait state, and when the waiting state has the space for the swapped out process to be incorporated, it would be swapped in back to the waiting state. Similar kind of a situation can arise for the ready queue. So over there also we have a suspended ready state where the process would be swapped out by the medium term scheduler if the queue is full and the process cannot be accumulated there. Usually the ready queue would not get filled up that much, but say a ready queue is filled and some higher priority process comes in. So in that case, the ready queue um, will have to make space for that process as it has a higher priority. So it will swap out the low priority process to the suspended ready state, and when it has space to accommodate that back in, it would go to the ready state again. So to understand this process test better, let's take an example of an ATM system. So in an ATM system, assume the ATM is a processor, and the people who would be using the ATM are processors. So now the so for using the ATM, we have a queue of people standing outside. Now as the turn comes, the people will enter. So the queue standing outside the ATM is the ready queue. Now they will enter the ATM and they, one by one, and they will do the process. And if and they would usually complete the process and terminate. But sometimes what happens, like if a person goes in and for some operation he needs an OTP, which he does not have, and he needs to contact someone else. For this, he doesn't need a ATM machine to contact some other person, right? So what he'll do is he'll step out, he'll contact that person, and stay in line with him, and then uh, get back to the ATM. So this can be thought of an waiting case, where the process was executing, and then it realized that it requires some other resource which is not present in the CPU. So he will go get the required result from that resource, and then it will get back into ready queue, and then when it turns comes, it would execute successfully. So this is what it means by the ready state, running state, and the waiting state. So in the ready state, a process would be if it is ready to be executed. So whenever it gets the chance to execute, it would use the processor and execute it. While in waiting state, we are waiting for some other device to be used to produce a following operation. So once that operation is done, it will go to the ready state, and then it will be dispatched to the running state again. So in the running state, if the process terminates, it will go to the terminated state, and in the terminated state, it would deallocate all the resources that were allocated to it prior. So since it has completed its execution, it no more needs those resources that we had allocated at the time of process creation. So we'll deallocate them and free those resources for other processes to use. So now let's see at the schedulers that we just discussed. So the long-term scheduler selects a process created from a pool of processes to the ready state, and it controls the degree of multiprogramming. It is relatively slow and less frequently used. The short-term scheduler selects the process from the ready queue based on the scheduling algorithm and gives the running and gives it to the running state. It is relatively fast and frequently used. Medium-term um, um, scheduler swaps the processes to the suspended state. Due to some reason, if the ready queue is full and the waiting queue is full, the new process cannot enter into those queues. So since there is no space available, the medium-term scheduler will suspend that process by swapping it out to the suspended states, and when the spaces are available in the respective queues, it would be swapped in back to the queues. There are two types of scheduling, primitive and non-primitive. In primitive scheduling, the process can be interrupted and will be forced to give the CPU. An example of this can be like if a higher priority task comes, then the current process will have to leave the CPU for the higher priority task to execute. And a non-primitive scheduling is like the running process keeps the CPU until it voluntarily gives up the CPU. Now, the term here voluntary means like the process will voluntarily give the CPU if it exists after its completion, or goes to the waiting state, like due to some IO request or some resource request that it has made. Process scheduling. The main objective of scheduling process is to maximize the CPU utilization and throughput, along with minimizing the waiting time, response time, and the turnaround time. To meet these objectives, the process scheduler selects a process from a pool of available processes and executes it. The selection of process is done based on different scheduling algorithms. To help with the process scheduling, there are few queues called the scheduling queues. First is the job queue. As the process enters the system, it is kept in this queue. This queue contains all the processes present in the system. Next is the ready queue. The processes that are present in the main memory and are ready and waiting to get executed are kept in this queue. These are the processes that will execute as soon as they are allocated the CPU. The next is the device queue. This processes this contains the processes that are waiting for an IO device or input-output operation to be performed. So, this is a diagram which represents the different various queues. So, the squares here represents the queues, and the circles are the ones which represent the resource they are using. So, so we have the job queue, from where the process would be selected and moved to the ready queue, and then from the ready queue the process would go to the CPU, where it will be getting executed. While executing, if it requires some IO request, it will go to the IO queue and complete its IO request and go back to the ready queue. Now suppose it requires a child to be executed or a sub process to be executed, it would go to a fork a child queue, and then when the child executes, it will go back to the ready queue. Similarly, in case of an interrupt, when the interrupt occurs, after the interrupt is over, it will go to the ready queue. So there are various scheduling algorithms that the schedulers use. So first come first serve, which is FIFO, which works on FIFO, like first in first out. So as soon as the process that comes in first will be executed first. Then there is shortest job first. So this in this the process which requires CPU for a smaller amount of time, which has a smaller burst time, would be executed first, and then the process having a larger burst time would be executed. Shortest remaining time first is a primitive version of the shortest job first algorithm. Priority scheduling is basically like each process would be given a priority, and the process which is having the highest priority would be executed first, and the process having low priority would be executed at the end. Round robin, in this the processor would allocate a time quantum, like a few specific units of time, say 3 milliseconds. So for 3 milliseconds a particular process would be executed, and then it would shift to a next process. So it would keep on going there, going round and round in a round robin fashion, so that each and every process gets a chance to execute. So in round robin, the response time of the process would be small. So then we have multiple queue. In this we'll have multiple queues maintained. And each queue will be having a different algorithm, scheduling algorithm. So suppose the first queue has a round robin, the second queue has FIFO. Then if the process is not completely executed in the first queue, it would be transferred to the next queue, and if it is executed successfully, it would be terminated. Then we have lottery scheduling. In this, we will be picking up processes at random and executing them. So that's all about processes. I hope you understood. You have a brief idea of what are processes in OS, and what is a process control block, which describes the process. What are the different states in which the process would be existing, and what is process scheduling. Thank you.